9,500 citations. He is also a senior member of IEEE. So with this, I am welcoming Dr. Ashok Kumar Das to deliver a talk on blockchain technology and its application to the IoT-enabled Internet of Drones for security, data delivery, and collection. So please.
Yeah, so thank you very much. Yeah. Is my slide visible to all?
Yes, sir.
Yes, sir.
Okay, so again, I'm continuing from the last session that I took yesterday. And today that we'll talk about uh, aspects of blockchain technologies, and also that blockchain technologies, how it can be applied in various applications apart from Bitcoin and cryptocurrency. And as a result, I'll talk about one of the applications or case study where this blockchain technology can be applied in IoT-enabled Internet of Drones applications in order to secure data delivery as well as collections mechanisms. So you can get all my informations from this URL. This is the institute URL, and this is the personal Google site URL. And also that for any clarifications, any doubts, so please let me to know through my email address ashok.das@IIT.ac.in. Okay, so the today's that talk is divided into two parts. In the part one, I'll first talk about the blockchain technologies and how this blockchain technology can be applied in different potential applications. Then in part two, I'll talk about one of the case study where we can apply the blockchain technologies for 5G based IoT enabled Internet of Drones environment for securing data delivery and collections. So first of all, let us talk about the blockchain technologies and its various applications. Now, first question is that you know that what blockchain. So I'll go very briefly in order to set the background, and also that I'll show that how all the cryptographic primitives that we have discussed yesterday can be embedded in the blockchain technologies. Now, if we see here that blockchain contains the two words, one is block, another is chain. So then what is the meaning of block here? Block means that we refer to digital informations which are put in the blocks. And obviously the blocks needs to be stored somewhere else. For example, if we want to store the blocks in some public domain, for example, in cloud database, so that will constitute a chain. And in case of the blockchain, multiple blocks, they are chained together and put in the public domain. As a result, a digital information is stored in forms of blocks, and it is also linked in a chain form. So hence the name constituted as the blockchain or chain of blocks. So since it is a chain of blocks or blockchain, that blockchain should start from some place. The first block that is created in the blockchain has a special term or name which is known as the genesis block. So therefore the genesis block is the first created block, in the blockchain. Now you can visualize that there is a very similarity between blockchain and simple linked list. Now, as you know that in the simple linked list, uh, you can always have the privilege to delete any node from the list. You can insert node at any place in the list. Even you can modify the data in nodes or blocks in the list. But whereas in case of the blockchain, so once a block is inserted into the chain or blockchain, that block cannot be modified, deleted, or even partial data cannot be updated. So that's why that one of the property that we'll see here, blockchain is immutable. That means that once a block is inserted in the blockchain, that cannot be tampered with that. So this is task is typically done by a protocol which is known as the consensus protocol, known as the agreement protocol, by which say there is a distributed networks of theirs, there are several nodes of theirs, and if the majority of the nodes they agree on adding a block in the blockchain, then it will be done, and after that the inserted block cannot be tampered with that. So next questions will come that why we need blockchains. So there are several reasons of this, that why that blockchain has gained much popularity in recent years. And one of the things would be noted that blockchain is not a new technology. Rather than we are reusing the blockchain technologies to secure various systems in applications. So first reason that is that it is not owned by any single entity. It is decentralized in nature. So which means that a block or piece of information that is stored distributed manner in each and every server in the network. Though we are storing the redundant data, but it is stored each and every that server in the network. As a result, if somehow one server goes down, then the other server will be there as backup to provide the same block or informations. Second thing is that data is cryptographically stored inside, that will show that with the help of the cryptographic primitives, it is possible to protect the data which are known as the transactions. Either we can encrypt the transactions put in the block in case of a something known as the private blockchain, and even it is the public blockchain, though the transactions are put in plain text in the blocks, but due to applications of the cryptographic hash, block hash, or elliptic of digital signatures, market root, etc., a block is cryptographically protected. That means that no adversary will be able to change the data inside a block. Thus, the blockchain is immutable, which means that no one can tamper with the informations that is stored inside the blockchain. So another good property that we'll see it here, that blockchain is transparent. So what does it mean? That suppose that I put a block in the blockchain, in later time I can always verify that whether my block or data has been put properly or modified or not in the blockchain. So this kind of transparency is there in the blockchain, which meaning that anyone can track the data if they want to do that. So thus that regions are, it is decentralized natures, it is cryptographically protected. As a result, it provides immutability and also it provides transparency. Thus, there exist three parts of blockchain technologies. So first pillar we are calling as the decentralizations. So the once the informations uh, is stored in the blockchain, that meaning that the information is not stored by any single entity. So hence everyone in the networks own the informations. Second is known as the transparency. So anybody can verify the transactions or digit informations that are put in the blocks. Then that last pillar is known as the immutability. So which means that uh, nobody that can tamper with the blocks or data that is already put in the blockchain. Now that we'll see one of the example. So here that cryptographic hash functions can be applied in order to achieve immutability property. Say for example, say if you are having say input say high, and if we apply say SHA-256 hashing algorithms, which is known as the secure hash standard algorithm 256, it will provide the 260 bits hash output. Say in it is replaced in the decimal format. Say welcome to say blog Greek. Uh, Glad to have here you. Then that hash value will be as follows. Now suppose in the second example, say there is a block or transactions that this is known as that this is test, your hash value is like this. Now if someone try to say modify these transactions uppercase t to lowercase t here, and simple modifications will raise completely different random hash output. So this is one of the property of the one hash function is that it is very sensitive even to small perturbations in input of for a hash functions. Thus, if an adversary tries to modify something, it will be detected during the verifications because that will make completely random hash output for the modifications. Then the blockchain networks and nodes can be maintained that with the help of a special kind of networks, so which is known as the P2P network or peer-to-peer network. So what is peer-to-peer network is that every node in the networks can communicate to any other nodes in the networks. Say for example, if there are n number of nodes are there in a P2P networks, a node can communicate with remaining n minus 1 P2P nodes in the network. As a result, we'll have that NC2 that is n minus 1 by 2 possible links in the networks. Therefore, that nodes in such kind of networks are considered as individual computers where they will take some inputs and performs or executes a functions on them. Finally, they will produce some output. And this blockchain, whatever we are going to discuss now, it will use this kind of special kind of networks that is known as the P2P networks So where the entire workload of the systems are partitions or divided among the participants, and the participants are equally privileged, which are known as the peers. So therefore, in a peer-to-peer networks, every node is given the equal privileged. As a result, that there is no longer a single server failure in case of the blockchain. If even a server fails, then other server will be there to take the backup in the system. Thus, there are several distributed and decentralized peers are there in case of the blockchain technologies. Now, based on the applications, we can divide a blockchain into the three categories. So, first category is known as the public or permissionless blockchain. So, under this category, anyone has a right to say join the networks, access to the service to the network, send, verify, receive the transactions of the blocks in the blockchain in order to create a consensus known as the agreement. So therefore, consensus is an agreement protocol by which if the majority of the nodes in a peer-to-peer networks agree to add a block after verifying that block as valid, then the block will be added in the network. So one of the wildly successful permissionless blockchain is Bitcoin or cryptocurrency, in which, say for example, traditionally suppose Alice wants to send some money, say dollar X dollar to Bob, then in traditional way that Alice has to do the transactions by some trusted third party known as a bank. But in case of the Bitcoin, that third party is not involved in the communications. Rather than involving the third party, what Alice will do that Alice will create a Bitcoin and that Bitcoin will be sent to the Bob directly. And to keep the record transparent, that Bitcoin will be put in the blockchain. So that is one of the example of permissionless or public blockchain where we can utilize that one. Then the next category is known as the private or permissions blockchain, in which the owner of the network that will decide which type of nodes needs to be assigned the rights to access, transmit, receive, join or verify the block in order to create a consensus between the nodes. See, one of the that example is that where we can use the private or permissions blockchain, say for example, healthcare applications or military applications. So in case of healthcare applications, that most of the data are very private and confidential. For example, a patient's that medical history or data informations is very private and confidential. We don't want to reveal such kind of information or transactions in public. So hence, all the transactions in case of a permissions blockchains are encrypted with the help of the public key of the that basically known as the owner of the block. Now, there could be other type of applications of the blockchains where it could be a hybrid or consortium type blockchains, in which all the transactions need not to be all public, some of also confidential. So hence that in case of the hybrid blockchain, that some transactions are encrypted because they are confidential and private, and others transactions will be unencrypted that can be seen by in public. Say for example, we can take one application, say for example, intelligent transportation systems in a smart city where say several vehicles uh, will go in some road in a smart city. They will form clusters, dynamic cluster. They will communicate each other say securely, pass the informations. For example, if there is an accident takes place, then that nearby vehicle can make a transactions of accident place, severity of the accidents, and gather all the informations. Can these transactions can be sent securely to the nearby roadside unit. Roadside unit can send to the nearby a server or say fog server. Then that those transactions can be put in the blockchain. And there could be say some confidential informations. For example, if there is a serious accident takes place, that informations uh, can be made private in that blockchain. So for that reason, say for example, uh, those kind of transactions can be also encrypted. Now say let us look at one of the scenario. So how to make a block in case of the public blockchain, private blockchain, as well as consortium. Now, just like that, you are having the internet header, that protocol, that IP header is there, or IP packet. Say, analogous to that, say, for example, we are having something known as the block. Block consists of the two parts. One is known as the block header, another is known as the block payload or transactions. Now in block header, so we it typically block header consists of these following fields. In consist of the block versions, which is a unique serial number or integer value, previous block has. So whatever previous block was there, that hash of that block will be put here, so that it will form the chain with the incoming blocks put in the blockchain. So as a result, if somebody say try to say modify some transactions because of that previous block has and current has value, that attacker needs to also change the previous block. That means that all the previous blocks needs to be changed, and also the future blocks that has value needs to be changed. That is not possible. Then marklet root is there. Marklet tree is a special kind of complete blank binary tree where the root contains the hash value of all the transactions. Then the block type can be defined the public, private, or hybrid. Then timestamp, it will give the time when that block was created by the block owner. Then the owner of the blocks, say some identity of the block owner will be there. Then the say public key of that block owner or signer will be there, and this public key will be used to verify the signature that we have already discussed yesterday, something known as the elliptic curve digital signatures algorithms, which will be used to verify the signatures. Now if we come to the block payload in case of the public blockchains, so here all the transactions are put in that clear text, they are not encrypted. Then we will compute the current block hash, so which is the hash of all the block headers values as well as block payload. So once that current block hash is computed, we will compute the signature on block using the elliptic curve digital signatures algorithms. which is known as the B sign. Now, if we come to the private blockchain, it has similar structures. Only the exception is that in case of the block payload, your all the transactions there encrypted and encrypted with the help of the public key of the block owner, so that only the owner of the block can decrypt the transactions, encrypted transactions, with the help of his or her own private key. So therefore, encryptions here it will be done using the elliptic curve encryption and decryption mechanisms. Then we are having the current block hash, which is the hash of the block headers fields as well as the encrypted transactions fields. Then finally we'll compute the elliptic curve digital signature on the current block hash to have the block signature. Now, similarly, that for the consortium blockchain, it has the similar structures. Only the change in the block payload is that some of the transactions can be encrypted when they are confidential transactions, and other transactions will be kept as clear text. So one thing is noticed that in this scenario, the verifications of a block takes place at the three levels. So first level is that known as the market route verifications. First, if the market route will be calculated on the transactions present on that block, if market route verifications passes successfully, then we'll go for the verifications of the current block hash. Again, we'll recompute the hash of block header and block payloads. If it matches with the computed current block hash, then finally we will verify block signatures with the help of the elliptic curve digital signatures verifications algorithms using the public key of the signer known as the block owner. So hence, if all the verifications take place successfully, then a block is declared as a valid block, otherwise not. Now let us come to discussions where we will talk about uh, an agreement protocol which is known as the consensus mechanisms. So which can be used in order to verify transactional data among the nodes in a peer-to-peer networks. So there are several consensus mechanisms are there. For example, Byzantine fault tolerance algorithm is there. So the consensus will be taken as the valid one when if there are n number of nodes are there, out of n number of nodes, as long as one third of the uh, total number of nodes that even they are Byzantine failure or malfunctions or malicious nodes, and if the two-third of the at least two-third of the nodes are not Byzantine failure or not corrupted, then the consensus algorithms will give green signal to add a block or transactions in a peer-to-peer networks. But the most practical one is that practical Byzantine fault tolerance algorithms, which was designed after the BBFT in order to achieve high performance along with the impressive overhead runtime. So now let us discuss a little bit about what is known as the practical Byzantine fault tolerance consensus mechanisms. So suppose that we have a block that needs to be added in the blockchain, using some consensus mechanisms, let it be PBFT. So what are the steps are required here as follows? So first of all, that among all the nodes in the network, a designated node known as the leader needs to be selected, and that leader will be given a special name as the minor node. And these selections of the minor node or leader node can be done using some existing leader selections algorithms, or that simply we can choose using the round robin policy algorithms. So let us assume that a leader has been selected and leader receives a block with block adding request from any one of the nodes into the blockchain. Then what leader will do that? Leader now will send this block to every node in the network for proposing the transactions which are known as the uh, that is something known as the PR nodes. They are basically will verify the transactions. Now let us assume that every node in the peer-to-peer networks they receives the block. Now they will start verifications of the blocks. So again, the verification of the blocks will take place at the three level. First, verifying the marketability route. Next, verifying the current block hash, and finally verifying the signatures. If all verifications successful, then a peer node will send a valid reply for adding that block in the blockchain. Let us assume that the leader will receive valid reply message from its peer nodes. For that reason, that leader keeps a counter known as the receive counter. Initially it is 0, and that counter is incremented each and every time when a valid reply message is received from its peer node. Now let us assume that there are n number of nodes are there in a peer-to-peer networks. Out of n number of nodes, we are having NF known as the number of faulty Byzantine faulty nodes or compromised nodes in the networks. And if the conditions that R count exceeds to NA plus 1, which means that two-thirds of the nodes give the same reply in the network, then that block will be added in the network, that is in the blockchain. So this is something known as the practical Byzantine fault tolerance algorithms. So once this condition is met, the leader will insert the block in its ledger known as the blockchain, and also the leader will send a commit message or broadcast a commit message to all its peer node in the network. So after receiving the commit message from its peer nodes, that is the from the leader, all the peer nodes will add the same block in their respective local blockchains. So in that way, uh, a block is added in each and every that nodes blockchain. Now next there is a consensus mechanisms known as the ripple protocol consensus mechanisms, and this protocol is due to the Ripple company in USA, and Ripple has recently that funded that to that 12 institute in the world, And out of 12 institutes in the world that they have funded two institute in India, in our country, and IIT Bombay and fortunately Triple IT Hyderabad. And that's why we are having a center known as the Ripple Center for Excellence in Blockchain in Triple IT Hyderabad. And also I am an active member of that center. So they have funded us 7 crores that rupees in 5 years to promote research on the blockchain technologies and etc. So these Ripple protocol consensus algorithms, which is in short known as the RCPA, and it is a voting based consensus algorithms. So which is used to achieve high accuracy of a correct agreement in order to add a block into a blockchain. And here, what is the concept they have used that this is a voting based consensus mechanisms. So where every participants in the peer-to-peer networks, they maintain a list known as the unique node list known as the UNL. And where that each node in the list is treated as a trusted node. The protocol here is executed with the help of the following steps. So during the voting process, every participant will receive a transactions. Once the transactions is considered as valid one, then that node needs to integrate the transactions into a set or list node known as the candidate list. Then that every participant node that sends its own candidate list to the other participant nodes as a proposal. So therefore that in the voting mechanism, if each participant is receiving transactions, that transactions is added to a list known as the candidate list. Then periodically the candidate list is broadcasted to other participant nodes, which are known as the proposals. So once a participant node receives the proposal from the other nodes, then it will check whether the sender nodes belongs to its own that UNL list or not. And if that node belongs to the UNL list, then the node will verify the transactions with its local candidate list that is maintained by that node. And once transactions are valid, the transactions will gain a vote. And once a transaction gets more than 50% of the vote, it will be declared as the transactions enters to the next round. Now in the next round, there will be process, something known as the proving process. So this threshold value, 50% of the vote, will gradually be increased to the 60% until that it reaches to a threshold value of 80% of the vote. So once it reaches to the 80% of the vote, then the participants nodes records the transactions because it is confirmed by 80% UNL node to be added in the ledger nodes, and after that the transactions will be added in the blocks in a blockchain. So if we compare that practical Byzantine fault tolerance algorithms with the Ripple protocol consensus algorithms, one of the criteria is required that number of the nodes in the networks uh, that needs to be at least 5 NF plus 1, where NF is the Byzantine failure persisted nodes in the network. Now, initially, when that Bitcoin cryptocurrency they were there, the first that old that consensus protocol was invented, which was known as the proof of POW. The problem with the POW is that it is very, very expensive in terms of the time consuming as well as computationally very expensive, because during the voting process or mining process, each and every node they need to solve a very difficult mathematical puzzles which consume much power and much computational time. So this is why that in 2017 that Ethereum they suggested to replace that proof of work by another enhanced or efficient that mechanisms known as the proof of stack. So which was designed to mitigate the limitations of the proof of work consensus mechanisms in terms of either its energy, cost, or processing time. So that is there. Now let us take one example, a simple example of a Bitcoin. So here the a block creations and additions using consensus mechanisms, say for example, proof of work consensus mechanisms in a blockchain. So in this category, suppose that Alice wants to send some money to Bob. So therefore, Alice first initiate a transactions by creating a Bitcoin. Then the Bitcoin is being broadcasted among all the peer-to-peer nodes in the network. Say, for example, you applied that proof of work consensus mechanisms that all the nodes that validate the uh, transactions as valid. So that means that peer-to-peer network of nodes validates the transactions and user status using CPOW consensus algorithms. Once the transactions is validated, then it needs to be combined with other transactions in a block to create a new block of data for the ledger. And after that, the new block will be added into the existing blockchains. Uh, Once it is added, that will call as the this is permanent and unalterable, that is immutable. That block cannot be removed or updated with any other transactions. And in that case, we will call as the transaction is complete. So this is a typical Bitcoin transactions where Bitcoin will be created, then it will be mined using some proof of work consensus mechanisms. So then the transactions will be added to a block, and new block will be added in the blockchains. Now let us talk about that. We talk about Marklet tree root. So Marklet tree is a special kind of Marklet tree, tree binary, complete binary balance tree. So in which that all the transactions are put at the leaf nodes. So therefore, say for example, we are having transactions 1, 2, 3, 4, 5, 6, 7, 8. Now then what we'll do that first we will compute all the transactions hash value, say hash 1 for transactions 1, hash 2 for transactions 2, hash 3 for transactions 3, and hash of 8 for transactions 8. So once we have all the hashes of the transactions, then what it will be done, we'll compute the hash of 1 to using hash of 1 and hash of 2. Similarly, for hash of 3, 4, we'll compute hash of 3, hash of 4. Then once we have hash of 1, 2, hash of 3, 4, we'll compute hash of 1, 2, 3, 4. Similarly, that will compute hash of 5, 6, hash of 7, 8. Then using hash of 5, 6, hash of 7, 8, we are having hash of 5, 6, 7, 8. Finally, we'll have the hash of 1, 2, 3, 4, and hash of 5, 6, 7, 8. So this will constitute the Markle tree root. Now, in case of the blockchain, say let us take a very simple example. Suppose currently we are having a blockchain having three nodes, block 1, block 2, and block 3. Suppose that block 2 has the four transactions A, B, C, D. We have computed the market T root and store in the block 2. Now the question is that for each and every block, some of the transactions will be different. Hence, market root, because it the hash of the all the transactions, it will be distinct. So therefore, in general, due to hash functions applications, the market root for each and every blocks are unique and distinct. So next is that suppose that someone wants to verify whether a transaction is valid or not using the market root concept. Suppose that a block has four transactions W, X, Y, and Z, and someone wants to verify whether transactions Y is valid or not. So note that this market T along with the market T root is already linked in the block. So therefore that given a transactions Y, we need to only compute the hash of the transactions Y. So once we have the hash of the transactions Y, then we will fetch corresponding hash of the Z to compute the hash of YZ. And similarly, having the hash of WX already stored in the market tree, we'll do hash of WX and hash of YZ to recompute the market tree root hash of say WXYZ, and then we'll check whether the recomputed market tree root is matching with the store market tree root in the block or not. And if they match, that means that no transactions has been modified or altered by any adversary. Now, as you have told that, so in India, specifically in other countries, Bitcoin and cryptocurrency, they are not popular due to several issues, including the political issues, uh, because of involvement of the trusted third party and commissions also. So then the researcher thought that can we apply uh, blockchain in untraditional or other applications? So answer is yes. In recently, it has been shown that blockchain can be effectively used to secure other applications areas. For example, we can apply in the smart grid, healthcare applications, Internet of Vehicles or Internet of Drones, which are known as the unmanned aerial vehicles or drones. It can be also used in the food industry, supply chain management, smart manufacturing, and so on. So on. And due to this, there is a new name has come, just like Internet of Things. We are now having a name as the blockchain of things. And here I have the research team here. So recently that we have worked on the several blockchain technologies, and this is the first work that IoT transactions on vehicular technology that I'll take here briefly as case study in this session, and also that we design some supply chain management using blockchains, for example, for generic IoT environment, as well as drone, internet or drone applications that access control mechanisms using blockchain technologies that we have designed. Okay. So in the next part that we'll take about a case study, uh, which was a collaborative work with Professor Pascal Lorenz from uh, Paris and Professor Maman Alajib from Australia, and it was published in a very highly reputed forum, which is known as the IEEE Transactions on Vehicular Technologies. So this was published recently in 2020. So I am going to discuss this case study in this part. So before that, if we have any questions, any doubt, probably that we can take before going to that. So participants, do you have any questions, anything? We can take it. Any questions? Anybody has any questions? Yeah, so do you have any questions, anything so that we can take? Otherwise, that I can move into the next part.
Participants, do you have any question? Sir, I think there is no question. We can.
Okay, yes, sir. Now we now talk about this case study here. So first of all, let me to give a very big overview. So what is known as the Internet of Drones? And it is treated as a layered network control architectures where the drones can be deployed in some flying zone, some partition zones known as the flying zones. So sometimes that we also call drones as the unmanned aerial vehicles, UAVs. Also, they are called also the drone, and they are responsible for controlling airspace, and also they provide various navigations activity support. Now, earlier that drones are applied to certain areas, but fortunately that in recent years there is a significant increase of the commercial drone applications. So that's why there is a broadcast focus that there will be soon a 100 USD billion market opportunity in futures that will be based on drones. So as a result that we now see the several applications of drones, either it could be say military applications, it could be say news gathering, for example videography and photography, particularly in COVID scenario, that drone can collect videography from certain areas, photographies for certain areas, can do the news gathering. For example, in agricultural field, we can use the drones. Logistic deployed surveillance purpose we can do in a smart city. Say Drones can be used to deliver medicines in hospitals or at home, door-to-door uh, delivery, traffic monitoring applications, and so on. So therefore, drone has numerous applications. So here, drone can be deployed, and they can be given their service efficiently. So next question is that why do we need at all data, secure data delivery and collections mechanisms? Now this is due to the things that, say for example, a drone delivery service is not new now. It has been used, say for example, London, which exchange of the say packages, so weighing up to say 500 grams. In addition, you know that there is a company DHL of German company. They also use the drones to deliver the emergency delivery of say high priority goods like say medicines to remote areas. Now, in general, the delivery systems in an IoT environment so works as follows: that based on trust that build among the delivery service provider as well as their customer. So as a result, that is service provider uh, assumes that their customer will not repudiate or do not do fraud the delivery confirmations after successfully delivered the items in their proper destinations. And on the other hand, the customer also need to trust that service provider will not say deliver an item without presence of them or deliver an item in front of door stolen. But now in practice, such kind of trust do not work always because it is very hard to maintain the responsibility. So in such scenario, it has been shown that if we apply some security protocol in the internet of drones in order to make the trust management systems automatically, then it is the best solutions. And towards this achievement, we designed a secure data delivery and collections protocol with the help of the deployed drone in such scenario. So since the drones also communicate over open channel or public channel, there will be several that attack possibilities by the attacker. Either that, say for example, a replay attack can be done, man in the middle attack can be done, in-person attacks can be done, privilege insider attack can be done. Most that dangerous attack is known as the physical drone capture attack. For example, a drone can be physically compromised, and all the informations that are stored in a drone's memory can be known to the attacker. The attacker can reuse those credentials to compromise the other parts of the networks using that drone information. And those kind of attacks are very serious. They should be handled carefully with the help of the design protocol. So in this scenario, that case study that we have taken, one of the 5G based uh, IoT environment with the help of blockchain technologies, where there is an authority known as the registration authority who is responsible for registering the control rooms, and control rooms will be responsible for registering the ground station servers, and ground station servers they control the drones with the help of the control nodes rooms. Control rooms also registers all the drones deployed in a flying zone. So for example, if we take one of the applications, say for example, hospital applications, where the drone be deployed in a hospital, certain areas that medicines can be delivered to hospitals and so on. For traffic monitoring systems, the drones can be used to monitor the traffic in a particular area of the city and so on so on. Then what we have done that since the communication is secure, and informations are say the secret credentials. Therefore, we require the secure communications among say drones and GSS, GSS and control room, so that the informations in term of transactions that will come to the GSS, GSS form the blocks using those transactions, secure transactions, and those blocks will be mined in a peer-to-peer that GSS networks, and using some consensus mechanisms. We have used the voting-based practical Byzantine fault tolerance consensus mechanisms in order to add that block in the blockchain. So for that purpose, that in high level that we are having various phases. So first page is known as the system initializations page. So which will give that all the system related parameters. For example, we have used the elliptic curve based crypto systems here, elliptic curve parameters, base point, one-way hash functions, private public key based parameters using ECC. They needs to be initialized in this page. So after the registration page will be there. So which will be responsible for by the registration authority to register the control rooms. Control rooms will register the GSS as well as drones in the network. Then the access control page basically helps to establish the secure communications between a drone and GSS and control room, so that after their mutual authentication, they establish the session key. Using the session key, they can communicate securely the transactions, and once it is there, this is known as the secure data delivery and collections page. All the transactions are delivered, related transactions, collections related transactions, they are securely gathered by the GSS. Then that those transactions will be used to form a block, verify block, and add the block in the blockchain using consensus mechanisms. And finally, also we are having a page known as the dynamic drones addition page. So sometimes, as you have told, that some drones can be physically compromised. So hence, we need to also add some new drones in the network. So let me go very briefly that, and this is the overall process in the proposed mechanisms. So if you look at that, first the registration authority will be responsible for registering the control room. So for that purpose, the control room will first send a registration request to the registration authority. After verifying the credentials, it will grant the register the say the control room registrations and send the registrations credentials via the secure channel. Then that ground station server, the registration takes place. It will send the registration request to the control room. Control room will send the registration credentials securely to the ground station servers. And meanwhile, also that in offline mode, that control room will generate all the credentials for a drone. All the drones related credentials will be stored in its memory, and then it will be deployed in a flying drone. So next is that by will also see the procedure by exchange of the three messages, message 1, message 2, and message 3, and that they'll be able to perform access control page in order to establish a uh, session key between them. Using the session key, they can communicate all the transactions securely with the base stations. Once base stations, they say, collect data securely from respective flying zones from drones, then those transactions will uh, be created, and transactions will be used to create a private block. Here we have used the private blockchain because uh, the informations are credentials, confidential. So then we have used a consensus mechanisms, also give the consensus mechanisms where a first leader will be selected, Then the block will be sent to the leader. Leader will send the block to each and every peer-to-peer nodes in the network. After performing the consensus mechanisms, the same block will be added in the by the GSS in the P2P network. So in that way, the blocks are added in the blockchain center. Now let us look at briefly here that something known as the registration mechanisms for control room, ground station server, and drones here. So first of all, that registration authority will pick up, for example, elliptic curve parameters, base point, one hash functions. It will also select the private public key pairs, and also that it will create a certificate, and certificate is generated by only the registration authority known as the RA. Then these informations uh, are made public and store these kind of informations in the control rooms. After that, control room will pick up master key and its own master key public key pairs, and they will be stored in its database. So in a similar manner, registration of ground station servers will be there, and where the control room again, it will pick the identity of the GSS, certificates, and other parameters, and ground station servers will preload the pseudo identity of the control room, certificates that is generated by the, say, control room, and other informations that will be stored in there in its memory. So finally, the registrations of drones also takes place by the control room. So note that here we have used the certificate-based mechanisms, where the certificate is created by a trusted party using its own private key, so that the certificate cannot be generated by even the entity, those who are having possessions of the certificates also, because it requires uh, the private key of the that party who generated the certificate. So after that, deploying the drones and installing the GSS control rooms in the network, so there is a page known as access control page. So in which, say suppose a drone wants to communicate with the ground station servers securely, then what will do that it will first select a random secret, which is known as the temporal secrets. It will generate a current timestamp, then it will compute, say, hash value, then a public key of this hash value R1 prime. It will generate a signature on that R1 prime. Then it will send a message consisting of the, say, pseudo identity of the drone, that public key, the certificate which was provided by the control room, signature on that R prime, and timestamp. So once this message is received by the ground station server, it will first validate the timestamp. If the timestamp is valid, that means that this message will be treated as the fresh one. Hence, the replay attack protection is okay. Means there is no replay attack in this during these communications. Otherwise, the message will be discarded as the old message. It will be deleted. So next, that it will verify the certificates. If the certificate is valid, then it will verify the signature. If the signature is valid, then it will compute another random secret R2 temple secrets. Using the temple secrets and other kind of permanent secrets, say private key of the GSS, it will generate the R2 prime, its corresponding public key it will generate, defilement type key it will generate, then the session key between the GSS and DR will be generated here. Then session key verifier will be also given to the in the message MSG2. So once the message MSG2 is there, having the pseudo identity of the GSS certificate, BGSS is SKV, that is a session key verifier, and timestamp, then it will check the validity of the timestamp, certificates as well as signature. And if all are valid, then it will compute again the defilement type key using the public key of the GSS. It will compute the session key and also session key verifier. Then it will check whether the session key verifier is valid or not. If it is so, then it will send an acknowledgement message in the message MSG3. After this, after receiving the acknowledgement message, it will verify the timestamp. If the timestamp is valid, then it will recompute the acknowledgement and it will check the acknowledgement. And if it is so, then it ensures that both the parties, drone and GSS, they mutually authenticated each other. Now they are sharing the same session key for their secure communications. So this is the access control mechanisms by which drone and GSS can mutually authenticate each other and establish a session key for future secure communications. So next that we'll talk about the details of various transactions. So here we have considered that 4 kind of transactions here. So first transactions is known as TXCR request, and which represents a transactions among a control room and GSS. And it is treated as the data delivery request from a control room to GSS. Now, once GSS receives the data delivery request, it needs to convey to corresponding the drone in a flying zone. So therefore, the next transactions come as the GSSDR request, which means a transactions between GSS and basically something known as the drone. So therefore, it also denotes a data delivery request from GSS to drone in a flying zone, that is FZJ. So once the request has gone to the drone, drone deliver some items or good at the destinations, collect the delivery informations. Then that informations will form a transaction, something known as the transactions DRGS's response. So therefore, it is a data delivery or collections response from the drone to the GSS, and GSS will securely collect these transactions from the drone. And apart from that, say for example, there is an agricultural field or say transportation systems or surveillance purpose, drones will, with the help of the camera, drones will take several pictures or photography, and those data or transactions will be also securely sent to the GSS. So therefore, this type of transactions is named as the TX GSS data, uh, where it represents the transactions between GSS and drones, and it is a say collections message from DSS to drone in a particular that flying zone. This is the collection data collections message. So once these transactions are formed and it is received by the GSS, then what GSS has to do? GSS is to create a block. So therefore, this is the structure of the block that here it is shown here. So in which we are having the block header consisting of the block versions known as the beaver, previous block as known as the PBH. We are having the marklet known as the MTR, and marklet is computed on the all the encrypted transactions here. Then timestamp when this block was created, that creator of the block, that means that which GSS has created this block, public key of the signer, which GSS has signed the message, that is the public key of the GSS. Then we are having a block payload encrypted transaction since it is considered as a private blockchain. So suppose that GSS has TN number of transactions. So therefore, using the TN number of transactions is forming a block, and all the transactions are now encrypted with the help of the public key of the GSS. So after that, it will compute the current block as CB hash. So hash of all the block headers as well as encrypted transactions. So finally, that signature on the current block hash will be computed with the help of that elliptic curve digital signatures algorithms. So on the current block hash. So here that we have shown a typical structure of a block that is now ready to be added in the P2P GSS network. So obviously that we require uh, a consensus protocols or consensus mechanisms, so which will allow a block to be verified and then to be added in the blockchain. So therefore we have designed a voting based consensus mechanisms for block verifications and additions in a blockchain. So therefore input of these algorithms will be a block, and we are having n as the total number of GSSP nodes, and out of say n nodes, let us assume that nf GSS will be the number of faulty GSS nodes in the networks. So faulty means that either it could be power failed or it could be also malfunctions or also the corrupted nodes. Then output will be the commitment and additions of the blocks in the blockchains after its successful validations. Now, what is the first step is that we first choose a leader, let it be say GSSL, the available n number of nodes in a P2P GSS networks. And once a leader is selected, then suppose that that block has a that leader has a block, say block I, which needs to be added in the blockchain. So for that purpose, what the leader is doing, leader first generates uh, a current timestamp, let it be say TSGSSJ, say for each follower constant server node GSSJ, and then proceeds for voting process. So in the voting process, what leader will do, leader will first create a voting request message, and voting request message and generated timestamp will be encrypted using the public key of the Gunstone servers to whom it will be sent. Now this encrypted voting request along with the block, that is the block I that will be added, each now sent to each and every that participating that node in the peer-to-peer networks. Now let us assume that the message from the leader is received by each follower GSS node in the network. Say let it be let at timestamp TS star GSSJ. Then what that each follower node will do that it will first decrypt the voting the encrypted voting request with the help of their its own private key. So private key is known as the KGSSJ, to it will get the voting request as well as TSSJ. So once it has the TSSJ, it will verify the timestamp. So by means of verifying whether the difference between this timestamp and detailed timestamp is less than uh, some maximum allowable delay or not. If the timestamp is valid, then reply attack is protection is fine. Then it will verify the magnitude, current blockage, and signature on received block I. And once all the verifications are done, that successfully, then what that follow-on node will do, that follow-on node will prepare a voting reply message, vote repeat, and block verification status, BB status. After encrypting the voting request message, previously decrypted one, voting reply message, that block verification status, encrypted with the public key of the leader. So once a leader receives this kind of voting reply message, let us assume that leader has a counter known as the V counter, which denotes the valid vote counters, initiality 0. And for each and every valid response message from the responded follow-on node, it will first compute or decrypt the voting request, voting reply, as well as voting verification status. Then it will check whether voting request matches with the same voting request request which was sent earlier, and whether the voting reply is valid or not, whether the voting verification status also valid or not. If it is so, then it will set the counter, increment the counter. Now, as long as that V count exceeds to NFGSS plus 1, since this consensus algorithms is based on the practical Byzantine fault tolerance algorithms, so therefore we have used this bound here. Then it will send, the leader will send a commit response message to all the follow-on nodes. So what follow-on nodes will do, that they will add the block I in their respective uh, that ledger in the blockchain. Then with the help of the security analysis, we have shown in the paper that you can also look at the paper for detailed analysis. It is able to restrict that replay attack, man in the middle attack, impersonation attacks. So what impersonation attacks is telling that uh, the protocol is designed in such a way that uh, the attacker on behalf of either DOT or GS cannot initiate the communications to full other party. Privilege insider attack is also that during the registration process, either GSS or control room do not give sensitive information to the registration authority so that they can misuse it. Physical don't capture attack is there, but each and every drone is given the different informations. So therefore, if a drone is the compromised, that compromised drone informations will not help to compromise the other nodes in the network. So finally, we are having the ESL attack known as the E4ML, that secret leakage attack, which is very important attack. So which tells that for any access control or authentication protocol, that it is better to build a session key which must rely on not only that temporal secrets but also with the permanent secrets. Because see, based on one recent adversary model known as the CK adversary model, if an adversary that is able to hijack a sessions, then all the temporal secrets can be leaked. So if the session key is based on temporal secrets only, then session key will be compromised. But in our case, we have used temporal secrets along with the permanent secrets. So in that way, the session key cannot be compromised. Now there are several that security analysis techniques are there. So one is known as the heuristic or informal security analysis, which requires less mathematical techniques. Then we are having the formal security analysis, which requires the random oracle-based techniques. And last one is known as the uh, formal security validations or verifications using some automated software tool. Here we have used something known as the Avispa tool, which stands for the uh, security that automated validations of internet security protocols and applications. So we have implemented our access control scheme with the help of high-level protocol specific language, which is a role-oriented language, and that language is translated to the intermediate format, low-level language using this translator. And there are four backends are available in that Avispa. First one is known as the OFMC, second was ATSC, third one SATMC, and fourth one is DA4SP. And once we fed that intermediate format to any one of the backends, it will then provide output format. And output format will precisely tell uh, whether the scheme is secure or insecure. Now, if the scheme is insecure, it will also give the trace that where the attacker is able to modify some part of the message content so that the scheme becomes insecure. Therefore, this is one of the very powerful tool that will detect whether there is any attack in your scheme or not. So this Avispa is open access software tool, and this, if you look at here, so it is a big project which was designed that under that for that countries or something. So you can look at the Avispa. So this is the Avispa project. The This was actually that built by that artificial intelligence laboratory, Italy, Switzerland, France, as well as German. And also that in the Avispa library, you are having several that protocols. For example, if you know that Cabros protocol is there, uh, TLS protocol is there, they are all implemented using the Avispa library. And for your documentations, you can read HLPSL document or Avispa document, everything. Now let me give only a very brief overview that how we have designed our protocol here. Uh, so just to have the brief demonstrations here. I think it is not visible here, so should I go there? Okay. So therefore, you can also install the span tool there. Uh, Span tool is there. You can install. Either you can run from their web page, but sometimes that resource becomes very much restricted, and that's why you should probably that install in your local computer, and that will be done. Something like that way. Yeah, then I have to install, reinstall again. Okay. So there is a that because I this span tool is there. So if you look at here, so uh, where is that span? So download span is there. You will see the older version is there. Like so here, first of all, that say for example, if we use a Ubuntu, say Fedora Ubuntu, you have to first download this one. Probably it will take some time. So then you here extract. Probably it should work now. So also the installations, that things that is I am giving to you. So you can, if anybody is interested, how to basically that install the Avispa and other things that I am giving in the your chat box message. So please have a things, and also there is a YouTube link which will also describe all these things. Okay. This is the YouTube link is there. You can also look at the YouTube link also. So this link is there, and how to that install everything, the stepwise everything is listed here. So now it should work, I guess. So first of all, that you have to export these two things with your set path, span and Avispa package. Then you should run the span here. So if you see that now it has come here, and then you have to open the HLPSL file that what has been implemented. So for example, we are having here so then here part 2 Avispa programming, this is the file. So are you able to see this one? So the something, no, it is too small font size. I have to increase.
Yes, it is visible, sir.
Maybe it is more visible, right? So if you see that, we have implemented the roles for the registration authority. This is a rule-oriented language. It is a game theory based role that each and every role a player will means agent will play against the adversary. Just like it is the syntax or whatever you can read there, local variable, constant variable needs to be there. Then initially the state will be there, and transitions will be there. Transitions basically define the receiving a message, sending a message, taking actions, all these things. So this is for that the role registration authority. We have role for the control room. We have role for the GSS. We have role for the drone, and so on. Then we have to define role for the session. This is mandatory role, which is the composite, the basic roles combinations. Then it is the environment role, which will declare what is the intruder knowledge, what are the attacker knows, and it will composite of the sessions, and where the sessions it is based on the Dolevio threat model. An entity will play also the attacker role, intruder role. Then you have to also specify the confidentiality and authentication goal. Confidentiality means that which parameters are kept secret to whom an attacker does not know, and authentication means that how that message will be authenticated by others. So the currently that OFMC as well as ATSC, they support bitwise JOR operations, but if you use the bitwise JOR operations, they are not supported by other two ends, backends. So therefore, if you say compile with the OFMC, so you should get say here save result. The protocol is saved here. It will give the statistics everything. For ATSC, that it will also give the save results. Say for example, we also implemented yesterday. We also saw yesterday that something known as the DPLMN key exchange protocol. Okay, probably that thing is there in DPLMN key exchange protocol. We also showed that it was vulnerable to the man in the middle attack. Yeah. For example, say DPLMN key exchange protocol that is say implemented using this HLPSL language, whatever protocol, same protocol is there. And we have already told that this is insecure against the man in the middle attack. This thing that if you execute, and it is showing that this is unsafe, because this will give exactly how the intruder is able to that basically that modify by using the dummy nodes, etc., how the protocol becomes insecure. And also that there is the animator tool known as the say intruder simulation is there, that will give that how that intruder is say, modifying the message content, and how does it work, everything will give it. So therefore this will give your practical that test bed kind of things, where you can test whether a design security protocol is secure or insecure. Yeah. So that result has been displayed here. So then also that we have done the test bed experiment using the Miracle library. So Miracle library is a multi-precision integer and rational arithmetic cryptographic library. So here we have taken the two kinds of platform. Or first platform is known as the server platform. Say for example, GSS or Groundstone servers, that platform we taken. Then we have implemented each and every that cryptographic primitives, for example, hash functions, modular exponentiations, elliptic multiplications, elliptic point multiplications, elliptic point additions, binary pairing. Then we have run each and every primitives on for say 100 times. Then we have recorded maximum time, minimum time, then average time we have recorded here. Say for the drones, we have taken the Raspberry Pi, the kind of experiments. We have implemented each and every primitive and stored in the Raspberry Pi. Then from Raspberry Pi, the processors, we have run each and every primitive for 100 times. We have recorded maximum, minimum, and average runtime. So that those are the results we got under this Raspberry Pi setting, and you will see that under Raspberry Pi setting, it takes more time. Then we have done comparative analysis on the communication cost. We have measured how many messages are required, and what is the total number of bits required for each and every message. And as a result, for a scheme, we have seen that our scheme achieves significantly better than other schemes. We have also done comparative study on the computational cost uh, from the point of, say, smart device or drone cost, from GSS or server cost. We have also listed, say, what is the gain we are getting with respect to other schemes. So then we have done comparative study on functionality and security attributes, and you will see that we have compared with the three schemes. And our scheme is much superior because it is designed in such a way that it is resistant to ESL attack under the secret adversary model, which is the one of the very good functionality features. And also, in addition, it supports also blockchain technologies that solutions. So then we have done also the blockchain implementations. For blockchain implementations, that was done by my PhD students under the node.js JavaScripts, and they have implemented that our protocol, consensus protocols. And we have taken the two scenario. First scenario, you have taken the number of peer-to-peer GSS servers as the 5, and number of transactions per block taken as the 60. Then we have varied the number of blocks mined in the network, and based on the number of blocks mined, we have received that computational time in seconds. And you will see that when the number of blocks mined is more, computational time also significantly increases. This is because it requires a lot of communications in the peer-to-peer networks when the number of uh, blocks mined to be more. Then in the next scenario, that we have taken the case where the number of peer-to-peer servers remains same, but the number of blocks mined is also fixed 30. But in that case, we have varied the number of transactions per block. And also you'll see that if the number of transactions per block increases, computation time also increases, because that each and every that peer nodes needs to verify each block by means of verifying the marklet you wrote, your current block has, and signature verifications. So finally, that we have also tested real-time test bed experiment here. So for that one, that we have used client server model paradigm with the socket programming environment under the Python 3 language. And each drone is considered as a client, and Constellation server is assumed to be a server. And GSS is considered as a laptop kind of configurations under this environment. And Raspberry Pi configurations is taken for the drone. So then in our the lab that we have taken a drone. In the drone, we have installed a Raspberry Pi. We have implemented the whole protocol and storing the Raspberry Pi as well as server. Then we created a local area networks with the help of a router. So then the body that GSS or laptop will be able to connect securely with the drone by means of authenticating each other, establishing key, sending the informations. So then it was shown that how that drone and GSS they connect each other, and so for example, an image has been taken, image has been securely sent to the GSS. All these things are there. So as conclusion, so the we have first discussed blockchain technologies and its various applications. Then I have discussed taken a case study which is a novel blockchain-based secure data delivery and collections scheme for 5G enabled IoT environment, and it implements that provides the access control mechanisms, also provides the blockchain secure solutions. Then we have shown that it achieves better security and requires low computational and communication cost, and all these things. Yeah, so these are some of the references there. And finally, so thank you, and hope that it will add some value. And if you are seriously looking for research in the area of blockchain technologies. So now that we can have some questions before closing it.
So, thank you, sir. Thanks for your nice session. Any questions from audience or in the chat box? You can see some questions. So, how physical drone capture that will be avoided?
So first of all, that physical drone capture, we can't avoid it, because if adversary say drone is flying somewhere else, if it is hijacked and it is physically captured, your all informations are captured. So therefore, the scheme should be designed in such a way that even a drone is physically captured, adversary knows your informations, but those informations cannot be reused to for secure communications with the other entity in the network. So that is the best way to do, because once it is physically captured, we need to that discard that drone and needs to deploy the other or face nodes in the network.
Okay. Any other questions? Okay. If there are no questions, let's thank the speaker. Thank you, sir. Ashok Kumar, thanks.
Yeah, thank you very much. Yeah, thank you.
Thank you. You have given the platform for the Paris Patul. So thank you very much, sir.
Yeah, so thanks a lot. Okay. Yeah, thank you.
Yeah, participant, the next session will start at 3 o'clock. Thank you all. I request all the participants, please be interact with the speakers and take it advantage. Okay. Thank you.